AI agents are evolving into entities that can search for information, understand situations, develop plans, use tools, and perform real-world business operations. Looking ahead, we are entering an era in which multiple AI agents with different roles and capabilities will collaborate to achieve a shared objective, rather than relying on a single AI. This makes the control of autonomy increasingly important. How much decision-making and authority to act should we delegate to AI agents? If autonomy is too limited, AI agents will constantly wait for human approval and will be unable to make full use of their capabilities. On the other hand, if autonomy is too broad, incorrect decisions or actions beyond authorized boundaries could directly affect real-world operations and society. What we need is not to assign every AI agent a fixed level of autonomy in advance. Instead, we need a mechanism that evaluates purpose, context, risk, policy, identity, and the current state of trust at runtime, and generates the appropriate level of autonomy for that specific moment. In this video, we will explore the concept of autonomy control for the age of AI coordination, along with approaches for managing AI agent autonomy safely and dynamically. First, let us consider why controlling AI autonomy has become so important. Until now, generative AI has primarily received questions or instructions from humans and generated answers or content in response. AI agents, however, do more than generate answers. They independently search for the information they need, analyze situations, reason about them, and develop plans to achieve specific objectives. They can also operate external tools and systems, execute processes, and collaborate with humans or other AI agents when necessary. In other words, AI is beginning to evolve from something that simply answers questions into something that makes decisions and takes action. As a result, the challenge is no longer limited to whether an AI's answer is correct. Even if its decision is reasonable, does the AI have the authority to act? Should it be allowed to act autonomously in that particular situation? At what point should human approval be required? And how much authority should it be permitted to delegate to other AI agents? In the age of AI agents, we must consider not only whether a decision is correct, but also which actions should be permitted, under what conditions, and to what extent. However, imposing stricter limits on action does not necessarily guarantee safety. This creates another challenge. The more we prioritize safety, the more we may sacrifice the speed and efficiency that make AI valuable. AI agent autonomy involves an unavoidable trade-off between speed and safety. When autonomy is set at a low level, the range of actions an AI agent can perform independently becomes limited. Because a human reviews and approves each important operation, it becomes easier to prevent incorrect actions. At the same time, however, processing slows down, while the amount of human review and time spent waiting for approval increases. If humans must continue making every decision even after AI agents are introduced, the agent's capabilities cannot be fully utilized. By contrast, when autonomy is set at a high level, AI agents can make decisions quickly and execute a continuous series of operations. This improves operational efficiency and reduces the burden on humans. However, if a decision or its underlying assumptions are incorrect, that error will also be executed at high speed. And if its effects spread across multiple systems or AI agents, a small error in judgment may trigger a chain reaction and escalate into a much larger problem. What we need, therefore, is not to permanently set autonomy at either a high or low level from the beginning. In low-risk situations, AI agents should be permitted to act quickly and autonomously. As risk increases, the range of permitted actions should be restricted, and for critical decisions, control should shift to human approval. In this way, autonomy must be adjusted dynamically according to the objective, context, potential impact, and level of risk. However, autonomy is not a simple capability that can be represented by a single number. AI agents can exercise autonomy at different stages, from defining objectives, planning, decision-making, and execution to collaborating with other AI agents and learning from outcomes. To achieve both safety and efficiency, we must therefore break autonomy down into its individual dimensions and manage each of them appropriately. AI agent autonomy can be divided into 6 major dimensions. The first is goal autonomy. This represents the extent to which an AI agent can independently define, interpret, and adjust its objectives and priorities, rather than simply carrying out a predefined objective. The second is planning autonomy. This is the autonomy to develop the steps required to achieve a goal, select the appropriate information and tools, and revise the plan when necessary. The third is decision autonomy. This represents the extent to which an AI agent can evaluate multiple options and independently determine what should be done in the current situation. The fourth is action autonomy. This is the extent to which an AI agent can use external tools and systems to execute its decisions. It includes actions that directly affect the real world, such as sending emails, updating data, processing contracts, making payments, and controlling equipment. The fifth is coordination autonomy. This is the autonomy to delegate tasks to other AI agents, distribute roles, and transfer information or authority while working together toward a shared objective. The sixth is learning autonomy. This represents the extent to which an AI agent can learn from outcomes and feedback, and autonomously modify its future decisions, plans, and actions. Among these dimensions, action autonomy and coordination autonomy require particularly careful control. Action autonomy transforms an AI's decisions into real-world operations. Coordination autonomy extends those decisions and authorities to other AI agents. With a single AI agent, it may be possible to limit the scope of impact to that agent's own actions. In an environment where multiple AI agents collaborate, however, a single incorrect assumption or instruction can propagate across the entire network through chains of delegation. Future autonomy control must therefore manage not only what each AI agent is permitted to execute, but also the relationships among agents and the full chain of delegated authority. In an environment where multiple AI agents collaborate, not only correct information and sound decisions, but also errors can flow through the network. For example, suppose a planner agent makes an incorrect assumption about a customer's intent or the terms of a transaction. Based on that assumption, a coordinator agent breaks the process into smaller tasks and delegates them to a sales agent, a contract agent, and a payment agent. The sales agent prepares a proposal using the incorrect terms. The contract agent generates a contract based on those terms, and the payment agent proceeds with the transaction using the wrong amount or conditions. Each AI agent may be executing its assigned task correctly. However, if the original assumption is wrong, the system as a whole will reach the wrong outcome, even when every individual process is performed correctly. Furthermore, if the coordinator agent delegates a task to an inappropriate agent or grants more authority than necessary, an incorrect assumption becomes an incorrect delegation. As multiple AI agents act on that instruction, the result may be a coordinated failure, a cascading failure caused by collaboration itself. This cannot be prevented by managing only the performance or accuracy of individual AI agents. Who delegated what to whom, and for what purpose? What information and authority were transferred? How long does that delegation remain valid? And who is ultimately responsible for the outcome? In the age of AI coordination, autonomy must be controlled not simply as an individual capability, but as something that also exists within the relationships among AI agents. So, what mechanisms can we use to control autonomy at both the individual and relational levels? There is no single answer. Instead, the available methods can be organized into multiple approaches, each serving a different role. Approaches to controlling AI agent autonomy can be organized into 7 major categories. The first is fixed rules. This approach defines in advance which operations are permitted and which are prohibited through explicit rules. The second is permission and sandbox. This limits the data an AI agent can access, the tools it can use, and the operations it can perform through access controls and isolated environments. The third is human in the loop. This requires human review and approval for critical decisions and high-risk operations. The fourth is risk-based autonomy. This approach evaluates the potential impact of an action and the likelihood of failure, then adjusts the level of autonomy according to the degree of risk. The fifth is trust-based autonomy. This evaluates the current state of trust based on factors such as an AI agent's capabilities, track record, current context, and compliance with applicable policies. It then dynamically determines the range of actions that can safely be delegated to the agent. The sixth is multi-agent verification. Rather than accepting the judgment of a single AI agent without question, this approach detects errors through verification, comparison, and challenge by other AI agents. The seventh is monitoring and rollback. This continuously monitors the state of the system after execution. If an anomaly or unexpected outcome occurs, the process can be stopped or the system restored to an earlier state. Each of these approaches has its own strengths and limitations. It is therefore important to combine them according to the nature and risk of the action, rather than selecting only one. The first requirement is to define the boundaries that an AI agent must never cross, regardless of the situation. Fixed rules and permission and sandbox provide the foundation for those boundaries. Fixed rules and permission and sandbox are the most fundamental approaches to establishing boundaries that AI agents must not cross. With fixed rules, actions that are always prohibited and conditions that must always be satisfied are defined in advance, regardless of the situation. For example, an AI agent must not be allowed to make payments. Personal or confidential information must not be sent outside the organization. Transactions exceeding 100,000 yen must require human approval. Production data must not be deleted. Rules like these function as explicit safety boundaries that take precedence over the AI agent's own judgment. Permission and sandbox, on the other hand, use technical access controls to restrict the data, tools, environments, and operations available to an AI agent. For example, an agent may be permitted to read data, but not to update or delete it. It may be allowed to create a document, but not to send it externally. It may be permitted to execute a process, but prohibited from delegating authority to another AI agent. In this way, operations such as reading, creating, executing, and delegating are separated, and the agent receives only the minimum permissions necessary. The strengths of rules and permissions are that they establish clear boundaries, simplify auditing, and limit the scope of impact when a problem occurs. However, remaining within an authorized boundary is not the same as making the correct decision. Even within the permitted scope, an AI agent may refer to outdated information, misunderstand the situation, or select an inappropriate option. Fixed rules also cannot respond flexibly to situations that were not anticipated in advance. In other words, boundaries are necessary, but boundaries alone cannot guarantee that a decision is appropriate for the specific context. This is where human review and approval become necessary. However, if every decision is returned to a human, the speed and efficiency of AI agents will be lost. The key is not for humans to approve everything, but to identify which decisions require human involvement based on their level of risk. Human in the loop is often understood as a mechanism in which humans review every action taken by an AI agent before it is executed, but this increases approval delays and turns humans into a processing bottleneck. Furthermore, if the number of review requests becomes too large, people may no longer have enough time to evaluate each decision carefully. Approval may then become little more than a formality. What we need is not a system that requires approval for everything, but one that switches between AI agent autonomy and human involvement according to the level of risk. For low-risk actions, AI agents can be granted a high level of autonomy and allowed to execute automatically. Examples include searching public information, classifying internal documents, and preparing drafts. For medium-risk actions, execution may be permitted only when specific conditions are satisfied. The process is monitored, and the result is reviewed afterward. For high-risk actions, autonomy should be reduced, with human approval required before execution. Examples include sending official notifications to customers, updating important data, processing high-value transactions, and modifying contract terms. For critical actions involving human life, safety, human rights, serious privacy violations, or critical infrastructure, autonomous execution by AI agents should be prohibited altogether. In this way, as risk increases, AI agent autonomy is reduced and control is strengthened progressively, from monitoring and post-execution review to prior approval and, ultimately, prohibition. A human gate is not intended to stop every process. It is a mechanism for identifying the critical moments that genuinely require human judgment and concentrating human attention and responsibility where they matter most. However, autonomy cannot be determined uniformly based on task risk alone. Even for the same task, the appropriate level of autonomy depends on whether the AI agent has performed it reliably in the past, whether the current situation is within normal conditions, whether sufficient knowledge is available, and whether the applicable policies are being followed. This requires an approach that evaluates trust across multiple factors, including risk, and dynamically adjusts autonomy based on the result. Trust-based autonomy does not assign a fixed trust score to an AI agent. Instead, it evaluates each time whether a particular AI agent can appropriately perform a particular task under the current conditions. This evaluation primarily considers 5 factors. The first is past performance. This examines how accurately the agent has performed similar tasks in the past and what outcomes it has produced. The second is current context. This evaluates whether factors such as the current user, business environment, time, location, and target data are consistent with normal operating conditions. The third is task risk. This assesses the potential impact on customers, the organization, and society if the task fails. The fourth is knowledge quality. This determines whether the information required for the decision is sufficient, up to date, and obtained from reliable sources. The fifth is policy compliance. This evaluates whether the AI agent's plan and actions comply with organizational rules, laws and regulations, contractual conditions, and safety standards. Trust evaluation integrates these factors in relation to the current task and context to determine the level of trust at that specific moment. When trust is high, the range of actions permitted for autonomous execution can be expanded. When conditions are uncertain, monitoring can be strengthened or the scope of execution restricted. When trust is low, the decision can be returned for human approval, or execution can be prohibited. The important point is that trust must not be treated as a fixed score permanently assigned to an AI agent. Even an AI agent with an excellent track record should not be granted a high level of autonomy in an unfamiliar situation or for a task where it lacks sufficient knowledge. Conversely, for a narrowly defined task in a safe environment, greater autonomy may be permitted once the necessary conditions are satisfied. Trust, therefore, is not merely an evaluation of the past. It is an expectation that an AI agent can produce a desirable future outcome under the current conditions. As that trust changes, the autonomy granted to the AI agent must also change at runtime. However, even trust evaluation cannot predict every error before execution. If the evaluating AI and the acting AI share the same knowledge or the same incorrect assumptions, they may overlook the same error. Some anomalies and environmental changes may also become apparent only after execution. We therefore need to combine pre-execution verification by multiple AI agents with continuous monitoring and recovery after execution. Autonomy control requires both mechanisms that prevent errors before execution and mechanisms that detect problems and enable recovery afterward. First, a planner agent creates an execution plan. Rather than executing that plan immediately, a separate verification function or AI agent checks whether it complies with applicable policies. Next, the system evaluates risks such as the potential impact of the action, the likelihood of failure, and whether the action can be reversed. When necessary, multiple AI agents examine the plan from different perspectives, searching for contradictions, omissions, and dangerous assumptions. This is pre-execution validation through multi-agent verification. However, if the verifying AI agents share the same knowledge and assumptions, they may all reach the same conclusion and overlook a common error. Simply using multiple AI agents is therefore not enough. Decision independence must be maintained by using different information sources, different validation criteria, and specific roles responsible for challenging or disproving assumptions. Only actions that pass the required policy, risk, and verification checks are executed. After execution, the outcome and the surrounding environment are continuously monitored. If the system detects an anomaly or a deviation from the expected range, it stops the process and, where possible, rolls back to a previous safe state. The detected anomaly and the recovery outcome are then recorded and used to improve future plans, trust evaluation, and policies. Through this feedback loop, AI agents learn from execution outcomes and make subsequent actions safer. However, not every action can be rolled back. Information sent externally, completed payments, published content, and impacts on people or the physical environment may be impossible to reverse completely. Irreversible actions must therefore not rely on post-execution recovery. They require stricter control through pre-execution verification, a human gate, or complete prohibition. Multi-agent verification and monitoring and rollback do not replace preventive controls. Errors must be prevented in advance, actions monitored during execution, and processes stopped and recovered when problems occur. Together, these mechanisms provide multiple complementary layers of autonomy control. As we have seen, the 7 approaches address different types of risk. At the same time, each approach has limitations that it cannot overcome on its own. Let us now summarize the strengths and limitations of the 7 approaches. The strength of rules is that the conditions for permission and prohibition are clearly defined. However, rules cannot respond flexibly to situations that were not anticipated in advance or to changes in the environment. The strength of permission is that it limits the scope of operations available to an AI agent, reducing the potential damage if something goes wrong. However, it cannot guarantee the correctness of decisions made within the permitted scope. A human gate preserves human responsibility for critical decisions, but if it is applied too broadly, it can cause processing delays and approval fatigue. Risk-based autonomy allows controls to change progressively according to the level of risk. However, accurately assessing risk in unfamiliar situations or across complex chains of impact is not easy. Trust-based autonomy dynamically adjusts autonomy based on factors such as an AI agent's track record, current context, available knowledge, and policy compliance. However, if the trust evaluation process is opaque, it may become difficult to explain why execution was permitted. Multi-agent verification compensates for the blind spots of a single AI agent through cross-validation from multiple perspectives. But if those AI agents share the same knowledge and assumptions, they may fail to detect a common error. Monitoring and rollback can detect anomalies after execution and restore the system to an earlier state where possible. However, it has limitations when applied to irreversible operations such as payments, public disclosures, external communications, and physical actions. Each of the 7 approaches therefore has a clearly defined role, but none of them is sufficient on its own. What we need is a layered integration of multiple mechanisms, designed so that each compensates for the limitations of the others. Fixed rules and permissions establish boundaries that must never be crossed. Risk and trust evaluate the appropriate level of autonomy for the current situation. Critical decisions are returned to a human gate and, when necessary, verified by multiple AI agents. After execution, outcomes are continuously monitored. If a problem occurs, the process is stopped, recovered, and used as feedback for learning. However, if these mechanisms operate as separate systems, inconsistencies in evaluation and gaps in control may emerge. We therefore need a common foundation that works across multiple AI agents and external systems, integrating these controls into a single execution decision. That foundation is the Autonomy Control Plane. The Autonomy Control Plane is a shared foundation for managing AI agent autonomy in an integrated way at runtime. It does not assign a uniform, fixed level of autonomy to an AI agent in advance. Each time an AI agent requests an action, the control plane evaluates the conditions at that moment and determines how much decision-making and execution authority should be permitted. The first factor it evaluates is the goal the action is intended to achieve. Next, it confirms the role of the AI agent and the permissions it possesses. It then obtains the current context, including the user, time, location, and operational state. It also evaluates whether the knowledge used to make the decision is sufficient, current, and derived from reliable sources. Based on this information, it integrates the risk of the action, the current level of trust, and the boundaries that must never be crossed to determine whether execution should be permitted. The control plane returns 3 basic decisions. The first is act. When all required conditions are satisfied and the risk is within an acceptable range, the AI agent is permitted to execute the action. The second is ask. When the information required for a decision is insufficient, or when human responsibility is necessary, the system requests additional information or human approval. The third is stop. Execution is stopped when the agent lacks the required permissions, violates a policy, has insufficient trust, or conflicts with an absolute boundary. These decisions apply not only to actions performed directly by the AI agent, they also apply to database updates, operations on business systems, the use of external services, and the delegation of tasks or authority to other AI agents. In other words, the autonomy control plane sits between AI agents and external systems, evaluating every important action according to a shared set of criteria. It also monitors the state and outcome after execution and records a decision trace showing which conditions were evaluated, what decision was made, and which action was authorized. The outcome is then fed back into trust, risk, knowledge, and policy to update future execution decisions. The key is not to treat autonomy as a fixed attribute of an AI agent. Even for the same AI agent, different tasks involve different permissions and levels of risk, and even for the same task, the permitted level of autonomy changes when context changes, such as the user, transaction amount, location, target data, or quality of knowledge. In practice, the basic decisions of act, ask, and stop are therefore expanded into more granular levels of autonomy. Should the agent only be allowed to observe? Should it be permitted to make recommendations? Should it execute only with human approval? Should it execute under continuous monitoring? Or should it be granted fully autonomous execution? The autonomy control plane does not fix these autonomy levels for each agent. It determines them at runtime for each specific combination of task and context. Let us now examine the 5 levels of autonomy that the autonomy control plane can grant in practice. Level 0 is observe only. The AI agent may observe and record information and conditions, but it cannot make recommendations or take action. Operations for which the agent lacks authority, as well as actions that conflict with established boundaries, are restricted to this level. Level 1 is recommend. The AI agent analyzes the situation and presents options or recommendations, but the final decision and execution remain with a human. Level 2 is act with approval. The AI agent may create an execution plan and prepare the process, but human approval is required before it can take action. This level applies to tasks with a meaningful degree of impact, such as proposing discounts or making decisions related to contracts. Level 3 is act with monitoring. The AI agent is permitted to execute the action, while the process and its outcome are continuously monitored. If an anomaly or deviation from the required conditions is detected, the process is stopped and the decision is returned to a human when necessary. Level 4 is autonomous action. An AI agent may act autonomously when it possesses the required permissions, knowledge, and trust, and when the task's risk remains within an acceptable range. Examples include low-risk, thoroughly validated tasks such as presenting approved product information. The important point is that a single autonomy level should not be permanently assigned to each AI agent. For the same AI agent, presenting product information may be level 4, proposing a discount may be level 2, committing to contract terms may be level 1 or level 2, depending on the terms and transaction value, and operations for which the agent lacks authority remain at level 0. Furthermore, even for the same task, the autonomy level changes when factors such as the user, transaction value, target data, time, location, knowledge quality, risk, or trust change. For example, a discount within the normal range may be handled at level 2. An exceptional high-value discount, however, may be reduced to level 1, returning the decision to a human. Conversely, if the same process is performed reliably over time and sufficient evidence and trust are accumulated, it may eventually be raised to level 3 under continuous monitoring. In other words, autonomy is not determined at the level of the agent. It is determined by which agent is performing which task in which context. For every combination of task and context, the appropriate autonomy level, from level 0 to level 4, is decided at runtime. This makes it possible to grant autonomy progressively for specific tasks without approving all of an AI agent's capabilities at once. However, determining the appropriate autonomy level requires evaluating the quality of the knowledge flowing to the AI agent. We must also preserve an explainable record of why that level was selected and why the action was authorized. This is where knowledge flow and decision trace become essential. To safely increase AI agent autonomy, we need both the knowledge used in decision-making and a decision trace that preserves the decision process. Knowledge flow provides the foundation for autonomy. For an AI agent to operate with a high level of autonomy, simply having access to large amounts of information is not enough. We must determine where that knowledge came from. Is it still valid and up to date? Does it accurately represent its meaning within the business? How does it relate to other information and rules? And can it be trusted for the specific task? For example, even when an AI agent is autonomously answering questions about products, level 4 autonomous execution should not be permitted if the price list it references is outdated. Likewise, when reviewing a contract, human confirmation is required if the applicable version of the terms or the relationship with the customer is unclear. In other words, when knowledge quality declines, trust also declines, and the autonomy level must be reduced. Decision trace provides accountability for execution decisions. It records what the AI agent observed, the context in which the decision was made, the knowledge and policies that were applied, How risk and trust were evaluated, which autonomy level was selected, which action was executed, and what outcome followed. This creates more than a simple log stating that the AI performed an action. It makes it possible to verify afterward why that action was authorized. Before a decision, knowledge flow delivers reliable evidence to the AI agent. After the decision trace preserves the connections among that evidence, the decision, the action, and the outcome. The execution outcome is then fed back into knowledge and trust to update future autonomy decisions. However, in an environment where multiple AI agents collaborate, recording the judgment of only one agent is not enough. Why did one AI agent delegate a task to another? What purpose, authority, and constraints accompanied that delegation? And is the receiving AI agent permitted to delegate the task again? These relationships and flows of delegation must also be controlled and recorded. For this reason, requests between AI agents should be treated not as simple messages, but as explicit delegation contracts. In AI coordination, requests between AI agents must not be treated as simple instructions or messages. When one AI agent assigns a task to another, it transfers not only an objective, but also a degree of decision-making and execution authority. For this reason, requests between AI agents should be treated as delegation contracts. For example, when a planner agent delegates a task to an execution agent, the contract explicitly defines 6 elements. The first is purpose. This defines the objective the delegation is intended to achieve. The second is scope. This limits the task's operating range, including the relevant business processes, data, customers, and systems. The third is authority. This specifies the permissions granted to the execution agent, such as reading or updating data, sending information externally, processing payments, or assigning tasks to other AI agents. The fourth is constraints. These define the conditions that must be followed during execution, such as transaction limits, permitted tools, prohibited actions, and required human gates. The fifth is expiration. This specifies how long the delegation remains valid or which event causes it to expire. The sixth is responsibility. This clarifies which agent or human is responsible for the decision, execution, monitoring, and outcome. The execution agent may act only within the boundaries of this delegation contract. If the execution agent delegates the task to another AI agent, it must not transfer authority beyond what was granted in the original contract. For example, an AI agent that has received read-only access must not grant another agent permission to update data or process payments. If authority increases with each successive delegation, unintended autonomy escalation can occur. Redelegation must therefore preserve the existing level of authority or narrow it further. The decision trace also records who delegated the task to whom, which contract authorized it, and what actions were performed. This makes it possible to review the full chain of purpose, authority, constraints, and responsibility, even when a process passes through multiple AI agents. AI coordination must control more than the autonomy of individual AI agents. It must also control relational autonomy. Who can delegate what to whom, and how much authority can be transferred. A shared control plane evaluates both individual agent autonomy and relationships among AI agents at runtime. Autonomy is not a permanent authority granted to an AI agent once and for all. It is generated as needed by observing the situation, evaluating risk and trust, and granting only the authority required at that specific moment. As we have seen, AI agent autonomy should not be configured once and then permanently fixed. First, the system observes the current situation. It then evaluates the objective, role, permissions, context, knowledge, risk, and boundaries. Next, it evaluates trust, whether that AI agent can appropriately perform that task under those specific conditions. Based on the result, the system authorizes the appropriate level of autonomy. Should the agent only be allowed to observe? Should it be permitted to make recommendations? Should human approval be required? Should it execute under continuous monitoring? Or should fully autonomous execution be permitted? Within the authorized scope, the AI agent acts, while its decisions, delegations, actions, and outcomes are preserved as a decision trace. The system then learns from the outcome, updating knowledge, risk, trust, and policy to inform the next decision. Through this continuous cycle of observe, evaluate, trust, authorize, act, trace, and learn, autonomy is adjusted and developed with every execution. The goal is not simply to impose stronger control over AI, nor is it to prohibit every action and prevent AI agents from operating. What we need is to preserve the boundaries that must never be crossed, while generating the appropriate level of autonomy for each situation and continuously coordinating the relationships among humans, AI agents, and external systems. In an environment where multiple AI agents collaborate, we must govern not only individual agents, but also shared objectives, authority, knowledge, trust, responsibility, and the full chain of delegation. That is why the future requires us not merely to control AI, but to coordinate autonomy, grow autonomy by accumulating safe experience and verifiable performance, govern risk through absolute boundaries and dynamic controls, and preserve evidence of decisions and actions to build trust between humans and AI, and among AI agents themselves. Autonomy is not assigned. Autonomy is generated at runtime. Autonomy is not something we simply grant. It is something we generate at runtime to enable safer, more trustworthy action.